Hello and welcome to my channel. Today we will start with ASK, Amplitude Shift Keying. Remember what we used to do in amplitude modulation? The amplitude of the carrier wave was varied according to the message signal. Here also we are going to do the same thing, but the message signal will not be analog but digital. Let me write it here. In ASK, the amplitude of the carrier is changed or varied according to the message signal. Here the message signal is not analog but a binary coded. What we mean by binary coded is, let's say I have a binary vector here of some values. This is my binary vector and this is my data which I need to transfer or send to somewhere. For sending we are going to use the modulation scheme, and for the modulation scheme we require a carrier of very high frequency. Let me take a sinusoid of amplitude A. Here the frequency is Fc, which is of very high value. Binary vector can be represented in time domain if we know the bit time period TB. TB is the time period of the bit. This is a TB. This is TB for this binary and so on. Let me write it. It will be more clear. It is 1, 0 and 1. What we are doing here is, I am representing 1 with some voltage level. Let me say 5 volt and 0 with 0 volt. You can choose another voltage level according to your system. And this bit is on for TB and this bit is on for TB, off for TB. And it goes like this. So this is my B of T. And this is time. I have taken a carrier wave, a cosine wave of very high frequency. So this is carrier of very high frequency. Its amplitude is A, C of t with time period t. Now to perform modulation, we will use a technique called on-off keying. What is on-off keying? This will be our signal, the ASK signal or the modulated result. See, this represents a value when bit is high, that means bit is 1. So we will on the system or we will press on. So carrier is on and we can see the amplitude level. As soon as we hit 0, we will off the carrier. Remember, we are sending. Here the carrier is off means we are putting down the level of carrier to 0. That means, that shows that there is no information. No, that doesn't mean there is no. There is information which represents 0. That's all. So this is off. And the process goes like this. So this is my signal ST. I can write an equation for it also. What we are doing, we are simply multiplying the carrier and binary data. So I can write S of t in equation form as S of t as BT into CT. Okay. And what is b? See, it's this b of t cos 2 pi fct. This is my modulated result. And if we try to take the Fourier transform, this is my time domain information. Now if we want to take the time domain frequency domain, we should convert this into frequency domain by using Fourier transform. So this becomes S of f, and we know the Fourier transform of cos is 1 by 2 del f minus fc plus del of f plus fc. But since the del is multiplied with another quantity b of t, so that del becomes b. Let me write the equation: a of pi 2 b f minus fc plus b of f plus fc. This is my equation. Before analyzing this equation, we'll show you something here that will be quite helpful to analyze this equation. See this carefully. I have my binary data and I am concentrating only a 1-bit time period, only just 1 bit. So 1-bit time period is TB. Since it is 0, so this means that would be T by 2 and TB plus TB by 2. Now if I take the Fourier transform of this, a Fourier transform of a rectangular pulse is sinc pulse. This is my sinc, and to calculate the bandwidth, which we always go in a frequency domain and there we calculate. The sinc pulse goes on like this to infinity. That means bandwidth requirement is infinity. No. The information is present only in this part and the other part are useless. So this time period is in, if we are talking about in angular frequency, then this is 2 pi by TB and this is minus 2 pi by TB, and here also this is 4 pi by TB, and it goes like this if we are talking about the angular frequency. So to pass this, we only need to consider this, and bandwidth is only considered of the positive part. So this will be my bandwidth, 2 pi by TB. This will be my bandwidth. Since this is the same thing, so we are considering this only for bandwidth. We always consider the positive part, or if you want to take the negative part, then that will be also 2 pi by TB. This was an angular frequency, and if I write the same equation in linear frequency, then we will not get this 2 pi, we will get just simply 1 by TB and minus 1 by TB. And what is this? This was my time period for of 1 bit. So 1 by TB is equal to RB, and this is bit rate. This is bit rate. So for in linear time requirement, the bandwidth is of 1 by TB. Now we consider this equation. See, I did the analysis just for just 1 bit. Now I have the equation form ready. This shows that the sinc pulse we will get will be on two regions, one at plus FC and the other one will be at minus FC. If I draw it here, then minus fc will be here, it will delay, and plus fc will be here, it will advance. This is fc, this is fc. I told you that we only consider the positive part. So the positive part, this is just a replica, this is a mirror image, we are considering this. The positive part is this much, right? So bandwidth will be this much only. Okay, so this is fc, and this was fc plus 1 upon tb, and this will be fc minus 1 upon tb. This is all linear frequency we are talking about. So the bandwidth requirement will be this minus this, that will be 2 by tb or 2 rb. And this is an important thing to see. The bandwidth requirement is twice, so twice the bit rate. So this we should remember.